Hello everyone. Today I'm going to talk about flyback converter. So this is a continuation of the topic of buck boost converter. We studied buck boost converter in both CCM and DCM mode, and we saw the configuration, we saw all the waveforms. Now we're going to see another kind of DC-DC converter called flyback converter. It's also called isolated buck boost. The main reason it's called isolated buck boost because it uses an isolation between input and output. Well, this is not the flyback converter. This is the circuit I'm gonna use to explain how we basically build the flyback converter. But a flyback converter comes with an isolated transformer. Let's talk about this isolated flyback that the flyback converter comes with. So it uses the same symbol as a transformer, but it's a little bit different. It's actually totally different. So how a transformer works is that we have a primary winding and we have a secondary winding. Excuse me. They have different turns ratio. They have a turns ratio N1 to N2, for example. And we have a current going through here and a current basically gets out of the secondary winding. So we have current, at each time we have current in both of these coils or windings. But the way the isolation in flyback converter works is through something called coupled inductor. Okay, so this is like how usually you describe the coupled inductor. So we basically have two windings on the same coil. So you can imagine that you basically have two different sets of wires that you wind around the same core. Let's assume that, for example, one is a little bit thinner than the other one, so the resistance are going to be different. Now, if the inductance of this one is L1, the inductance of this one is L2, then these are coupled inductors. Okay, so let's assume that if we have current going through L1, then it builds a flux through this core, and the energy is going to be stored in the core of the inductor, in the magnetizing inductance. And once this current is cut, once this is basically there's a discontinuity in the current, then the energy stored in the inductor, it's going to be released in the L2. So that's how the coupled inductor in flyback converter works. We never have two currents both at L1 at L2 going through L1 and L2 at the same time. So what happens is that in the coupled inductor that's used in flyback converter, we have a configuration like this. Actually, I could have used the same thing. So let's just use the same method. So we usually model this with a magnetizing inductance coupled with an isolation transformer. So the way this works is that as soon as you turn this close, assume that this one is opened, right? So once you close this one, we have a current going through this loop. So the energy gets stored in the magnetizing inductance of the coupled inductor, right? But because this switch is open, no current can go through the secondary winding. Okay, so now let's assume that we have a synchronizing system that once you open this one, you close this one. Now what happens in this case is basically the current that, or the energy that got stored in this coupled inductor, in this magnetizing inductance, is now gonna release itself in the secondary winding. Okay, so this is the basic concept of how the isolation transformer in the flyback converter works. You have current in the primary side, energy gets stored in the magnetizing inductance of the coupled inductor. Then you have the discontinuity in the current is cut on the primary side, and the energy is gonna be released in the secondary. So that's how this conversion works from the primary side to the secondary side. So now a couple of things to mention is, first of all, the ratio between these inductances is gonna be N1 over N2 squared. Should know this from your physics, right? And as I mentioned, like, we assume that, let's say that this is S1 and this is S2. S1 is on and it's off, and when S1 is on, S2 is off, and then when S1 is off, S2 is on, right? If that's the case, what we end up with is basically, in the current that goes through the primary side, sorry for the shaking of the camera, the current that goes through the primary side, it's gonna be, first, let me just start with a minimum current. It's gonna be, actually, let's just start with 0, just to make it simple. So it's gonna go, I just wanted to show you the slope. It's gonna go with the slope of V1 over L, and it's gonna be 0 for the rest of it. Okay, and so this is I primary. And I secondary, can you guess how I secondary it's gonna be? It's gonna be 0 when switch 1 is on and switch 2 is off. And then after that, it's gonna go down with the slope of, what's the slope in this case? V secondary over L, right? Because we have V secondary over L, okay? Now, the way I draw this is exactly at the boundary conduction mode, because you see that it starts from 0, it ends at 0, right? We're gonna study this in both CCM and DCM, right? So for now, just like showed you,